Hello friends, welcome again to this today's session. Today we are going to learn about the energy of a plane progressive wave. Right, in the last lecture we have seen about the differential equation of a wave motion, how to write the wave motion in terms of mathematical equation, that is differential equation. And now today we are going to learn about the energy of plane progressive wave. So first of all, what is plane progressive wave? A wave which is continuously moving in a given direction, it is called as a plane progressive wave. And at the same time, a wave which is means at the head of the wave, the new waves are continuously forming, new waves are continuously producing, that is also the plane progressive wave. And in the plane progressive wave, all the particles of the medium performs or executes the simple harmonic motion. So such a wave is known as plane progressive wave. That means name itself indicates that it is having always the progress, it will be moving continuously in forward direction. And yes, the new waves are creating at the head of the wave continuously, and it will move continuously in a given direction, or in that way we can call this, means that there is a continuous transfer of energy in the direction of progression of the wave. That means energy is continuously propagating in the direction of propagation of wave, and such wave is known as plane progressive wave. And yes, obviously the particles always performs or executes the simple harmonic motion when we are talking about a plane progressive wave. So what we have to find here is energy of that plane progressive wave. Yes, we know what is a plane progressive wave, and now next task is to find its energy. How much is actually the energy is propagating or energy is transferring through the plane progressive wave, right? Okay, now again to start with this particular derivation, we have to take the help of our displacement equation, that is y is equal to a sine 2 pi by lambda vt minus x. Yes, this is what the general equation to represent the displacement of particle when it is performing simple harmonic motion in the medium, right? Yes, so the equation of simple harmonic wave is y is equal to a sine 2 pi by lambda vt minus x. This equation already we have seen several times in previous articles. So this is the general representation of a wave motion, simple harmonic wave. So it is, so y is equal to a sine 2 pi by lambda vt minus x. We know that y is the particle displacement, right, not the wave displacement. Now since y is a particle displacement, and to find the particle velocity, obviously we have to differentiate equation 1, we have to differentiate y, because rate of change of displacement with respect to time, that is your velocity, right? Your means yes, particle's velocity, and y is the displacement of particle, and we represent u, that is what particle velocity, and it will be dy by dt. Simply dy by dt means rate of change of displacement with respect to time. So to find the particle velocity, let us differentiate equation 1 with respect to time. Yes, that's what we are doing in this particular statement. Now here is what the differentiation, we know how to differentiate it. Again, in this case x is constant, and therefore u is equal to dy by dt. Okay, so here we have to differentiate with respect to time. A is constant, derivative of sine is cosine, so cos 2 pi by lambda vt minus x as it is. Again we have to take the derivative of this inner particular angle of cos sine. So to again in that case t is only here with respect to, or in multiplication with v, x is in addition, and that is constant with respect to t, that's why its derivative will be 0. And here in this multiplication we have 2 pi vt by lambda, and among that 2 pi v by lambda is constant, and therefore the derivative of t is 1 with respect to t. Therefore 2 pi v by lambda will be here as it is. A is already constant, and then cos 2 pi by lambda vt minus x, because sine's derivative is cos. So this equation already we have seen in the last video also, but once again that will give you the particle velocity u. dy by dt is equal to 2 pi v by lambda a cos 2 pi by lambda vt minus x, equation number 2. Very first equation we have named it as equation 1, and this is equation number 2. Again, yes, once you got the velocity, the next task is to find the acceleration. Again, you know, to find the acceleration, take the differentiation of velocity, rate of change of velocity with respect to time, that is what we call acceleration. So this is what velocity, and its rate of change means again d by dt. So what is the velocity u? So du by dt. This is what acceleration, it is denoted by small f. Okay, you can denote it by a, but already small a is here, so to remove or to not get confused between that and this, I have denoted it by small f. Okay. So, small f, that is acceleration. Moreover, obviously particle acceleration, it is rate of change of particle velocity du by dt, and we can call it as, because u is what, dy by dt, and therefore it is d2y by dt square. It is d2y by dt square, since it is a double derivative. Already u is dy by dt, and d by dt of dy by dt means d2y by dt square. So, yes, obviously we have to take the derivative of this particular equation 2 once more, and that is differentiating equation 2 with respect to time again. So, that will be acceleration f is equal to d2y by dt square again. Okay, equation number 2 is here. So, here 2 pi v by lambda is constant, a is constant, derivative of cos is minus sign, that is why minus sign will be there, and again derivative of this inner particular angle is 2 pi v by lambda. Already here 2 pi v by lambda, and this new 2 pi v by lambda, it will be 4 pi square v square divided by lambda square. A will be as it is, and yes, derivative of cos is negative, that is why negative sign will be there, and this term becomes sine of 2 pi by lambda vt minus x. Yes, that is what happened here. Look at this equation number 3. Why 4? Because 2 pi v by lambda was already there, and one more time it comes from this particular inner derivative by chain rule, and it will be minus 4 pi square v square by lambda square a sin 2 pi by lambda vt minus x. That is equation number 3, and it gives you the acceleration of particle which is performing simple harmonic motion, right? Okay. And why there is a negative sign, or what that negative sign indicates, or what that negative sign signifies? So, the negative sign shows that the acceleration is directed towards the mean position. That is what the nature of our simple harmonic motion. That is what the basic definition of simple harmonic motion. Acceleration is always directed towards the mean position, and that will be shown by this negative sign. Okay. So, from that also we can definitely say, yes, particle is performing, or particles are performing simple harmonic motion. Okay. So, what we got from the y, from displacement equation, it is very first equation. From that, we, after differentiating, we got equation number 2, that is velocity, and that is again we differentiate equation 2, and that will be equation 3, that is our acceleration, right. Now, how to find the potential energy? We have to find potential energy, because what is our target, what is our article name? Energy of a plane progressive. So, obviously energy means it is the sum of kinetic energy as well as potential energy. So, first of all we got the acceleration. From that let us see how to find the potential energy, and then we will talk about kinetic energy, and then add them together, it will be, or it will be the final answer, that is the energy. Okay. So, to find the potential energy, let us talk about work done. First of all, work done, and if we integrate work done, that will be the potential energy. Okay. We know that V is equal to integration W. So, let us talk about the first of all work done. So, to move the particle from its mean position distance at a distance or by the distance dy, work has to be done against the acceleration. Yes, because acceleration is, now let us consider this is the mean position and this is the particle. This particle, or we have seen like this, the wave will be like this. So, this is the mean position, and particle performing simple harmonic motion in this direction, vertical direction, upward direction. But what we have seen, yes, in case of the simple harmonic motion, particle are always pulled towards the mean position. That is what the negative sign indicates in this particular acceleration term. Acceleration is always directed towards the mean position, and if particle has to perform the simple harmonic motion, that means particle has to pull itself against the acceleration. Yes, against the acceleration. Acceleration is pulling towards the mean position, but particle has to perform the simple harmonic motion, it will pull against the acceleration, and that work done, because to pull that particle, the particle has to do some work, and that work done will be against the acceleration. Let us consider dy is the displacement through which particle has to displace from its mean position, and capital F will be the force required for that particular particle to move or to displace itself from the mean position. So, that is what we have considered, and therefore, displacement will be F into dy. Yes, we know that, sorry, not displacement, work done. We know that work done is force into displacement. So, how much is the force? F is the force and dy will be the displacement. That is why it is the work done for a particle to displacement, to have the displacement dy. Okay. So, here you can write the equation like this: dw is equal to F into dy. you can write like equation, dW is equal to F into dy. dW is what? The fractional work done or the work done by the particle to have the displacement dy, to have the displacement dy, and how much is the force required? This much is the force required, capital F dy dW. Don't write it as small f, because small f we have already used for the acceleration. So dW is equal to F into dy, you can write this, right? Next, once you got this, the dW is equal to F into dy, now what we have to find? The work done, total work done. But here we know this F is what? This F is what? Force, and force can be written, force F is equal to mass into acceleration. What is acceleration? We have denoted how? Small f. So force is equal to mass into acceleration. This is what by Newton's second law, everybody know this. But again this mass we have to write in terms of density. We don't want m here. We know the density of the medium, but we didn't know the mass of each and every particle. So therefore we have to express that mass in terms of density. So how is the relation between mass and density? Obviously everybody know rho is equal to m by V, mass per unit volume. Density is nothing but mass per unit volume. Now again work done per unit volume, here we have written in this case work done per unit volume. That means this volume will be 1 per unit, means take volume it as 1 per unit. So in that case mass is nothing but what? Density. If V is equal to 1, then rho is equal to m, then rho is equal to m. So by that equation, therefore we got here, I will write here as, you please write here, it is dW is equal to this equation. Okay, dW is equal to rho. Why rho? Because mass is equal to density. Here we have written per unit volume. So rho, then what is that? Mass. Yes, mass is equal to rho. And acceleration, what is acceleration? Now keep this acceleration from equation number 3. Equation number 3 is acceleration. Okay, and finally dy is as it is, dy is as it is, from this dy here and dy here. Okay, did you got this? What we have done here, we have used simply two equation. One is by our Newton's law, F is equal to ma. From that we have written force, this force is equal to mass into acceleration, but we have to express mass in terms of density. That's why we have considered mass per unit volume, that is density, and whatever work done we have to calculate, that is also we want per unit volume. That's why therefore the volume will be 1, and in that case mass is equal to density. So instead of mass we have written here density, and instead of this small f, mass is equal mass into acceleration. So acceleration is equation number 3. This equation number 3 we have substituted here, yes, as it is. Okay, you might have this difference, sir, negative sign is not substituted. Doesn't matter, we want to find the work done. Don't worry, we here the negative sign does not have any work to do. Okay, and this dy is as it is, displacement. Okay, that negative sign only indicates the acceleration is about or towards the mean position. Therefore the negative sign will be there. Here it is doesn't matter if we don't substitute it. So this equation will give you dW. Yes, this equation will give you dW, the work done for moving the particle from mean position to the displacement dy, by the displacement dy. Okay. Right. So again, now the total work done, that is what? dW. Now we want to find the total work done. So total work done, W is equal to, here you can write W is equal to, or I will write to this side, this is W. W is equal to integration from 0 to y. So dy is the fraction of small displacement, but if we want the total displacement, let us consider these two particular limits, 0 to y, and for dW, this is completely dW. Yes, integration dW will give you the total W, or that is total work done, and when we integrate within the limit 0 to y. But we know that a sin 2 pi by lambda Vt minus x. Look at the equation number 1. What is this? This complete, not this complete, but if we talk about a sin 2 pi by lambda in bracket Vt minus x, this is your y, that is what the initial displacement. So let us consider, or let us substitute in this equation that equal to y, and take the remaining things which are independent of y, take it are outside the integration. So 4 pi square V square by lambda square, and this row everything will be constant, and in bracket this a sine 2 pi by lambda Vt minus x is y. Here we have substituted, this dy is as it is and limits from 0 to y. Okay, right. So this complete bracket is constant with respect to y. And again everybody know this simple integration 0 to y into dy, it is y square by 2. It is like x's integration is x square by 2, same is here. So this bracket as it is, and integration, we just take integration here, and therefore what we get is 4 pi square rho v square y square by 2 lambda square. Let us cancel this 2 and this 4. So what we will get, 2 pi square rho v square lambda square, sorry, y square, and divided by lambda square, this equation number, and that is what potential energy. But again we have to substitute this y value. So therefore substitute that y value. Y is what? A sine 2 pi by lambda Vt minus x. Yes, here we have substituted it only for solving that integration, but finally we have to substitute that value, and after substituting that value, 2 pi, this equation 2 pi square rho v square by lambda a square sine square 2 pi by lambda Vt minus x, because it was what? Y square, it was y square, that is why it is whole square, a square and sine square 2 pi by lambda Vt minus x, because this is angle, do not make this its square, this is angle. Okay, sine square we have made here, no need to do that. Now this is what your potential energy, name it as equation number 4 and keep aside. Let us talk about now the kinetic energy. So kinetic energy, everybody know, half mv square. Yes, kinetic energy is half mv square, but v is here what? We are talking about which particular thing? We are talking about particle, and therefore particle velocity, that is why particle velocity we denote it by u, and it is u square, half mu square. Okay, right. Again we do not want this mass, per unit volume, we are talking about per unit volume, that is why instead of mass, can I substitute the rho? Yes, because when we talk about per unit volume, mass is exactly equivalent to density, and therefore here we got half rho u square, nothing else, do not get confused. It is our simple definition, half into m into velocity square, but here m is nothing but what? Your rho, density. So half rho u square. Again u we have already calculated, substitute that u from equation number 2 here, 2 pi v by lambda a cos 2 pi by lambda Vt minus x, substitute u, half rho as it is, take its square, then its square, here there it is 4 pi square v square divided by lambda square, rho was as it is, denominator 2 and this 2 will get cancelled, one more step we can increase, now a square as it is, cos square, and this angle will be same, the equation number 5. Simply taking the square of this and taking outside 4 and then cancel this denominator 2 and numerator 4, it becomes 2, and this will be equation number 5. So equation 4 is potential energy, equation 5 is kinetic energy. Yes, we know that once you got the potential and kinetic energy, to find the total energy, let us add them together and it will be the total energy. Total energy is equal to potential energy plus kinetic energy. So equation 4 is potential energy, equation 5 is kinetic energy. Let us go to the final slide. Then total energy per unit volume, yes, that is important, we have considered per unit volume, and therefore only the mass becomes density, or mass is equivalent to density. So total energy, potential energy plus kinetic energy. Now look at the equation 4 and 5, exactly same, right? These particular constant is exactly same, only here we have, one second, yes, here we have sine square and here we have cos square, remaining things are exactly same, and that is why we have taken directly common, all these constant factor common, and in bracket sine square theta plus cos square theta, because theta are exactly same, 2 pi by lambda Vt minus x, and we know that sine square theta plus cos square theta is always 1. So yes, finally what we got, equation number 6, and that is only this particular constant, because this square bracket becomes 1. So 2 pi square rho v square a square divided by lambda square. Again let us have some substitution, because we know that here velocity v is equal to nu lambda. Nu means what? Here frequency, but this also looks like nu, that is why we have denoted that n as or that nu as n. So velocity is equal to frequency into wavelength, v is equal to n lambda. So substitute here, if we substitute V is equal to n lambda, if we substitute V is equal to n lambda in this equation, so V square means n square lambda square, in the numerator n square lambda square, and in the denominator already we have lambda square. So this lambda and this lambda gets cancelled, and this n square only survive from the V square. So remaining 2 pi square rho a square as it is, and from that V lambda square get cancelled, and only n square will survive, and we got the little bit simple equation E is equal to 2 pi square rho n square a square, equation number 7, and that is what the total energy of the plane progressive wave. Okay. Now, yes, this is what the total energy we got, but let us talk about the average kinetic energy and average potential energy. Equation I think 4 and 5, yes, equation 4 and 5 are the potential energy and kinetic energy per unit volume, but what about the average kinetic energy and what about the average potential energy? So simply to find the average kinetic energy and average potential energy, yes, so the average value, if we take the average of this equation, one second. So if we take the average of this equation, all the things are constant. These 2 pi square rho density for that particular medium will be also constant, V is constant, lambda is constant, everything is constant, only the average value of this sine square, and in this equation only the average value of this cos square. So if we take the average value of sine square and cos square, so we know that we have the standard things, average value of sine square and whether it is cos square, it is always, anybody knows, it is always half. It is always half. So the average value of sine square and cos square is half, always right aside somewhere else. Average value, mathematics people might have know this, average value of sine square or cos square is always half. So the average value of sine square and cos square half means this particular bracket, or sorry, this sine square, instead of sine square we can put half. Okay. So again we substitute here V is equal to n lambda, and that is why this 2 and this 2 will get cancelled, and we got that pi square rho n square a square will be the average kinetic energy per unit value, and same will be the average potential energy per unit volume, pi square rho n square a square. We can find either these, okay, and then this one and the same. Now if we add equation 8 and 9, what we get? Yes, 2 pi square rho n square a square, that will be the average total energy of the particle which is performing simple harmonic motion in a plane progressive wave. That is why we can say it is the energy of a plane progressive wave. And lastly, let us consider, or suppose the area of cross section of a parallel beam of radiation is 1 unit and the velocity is of the wave is v. That means let us consider that the particular beam is traveling through this particular cross sectional area, yes, in this direction. Let us consider the wave is traveling in this direction. Let us consider the wave is traveling with the area of cross section, 1, area of cross section 1, and v is the velocity, yes, velocity of the wave. So obviously when we have to find the volume of this particular thing, how to find the volume of this particular parallel pipe or parallel beam? Simply how much is the velocity into the area of cross section, yes. So here that is what we have done here. Volume is equal to what is area of cross section? We have considered 1 unit area of cross section, and v is the velocity. So volume is equal to area of cross section into velocity. That is why volume will be only v, and energy transfer per unit area per second. Now energy transfer, here it was total energy, this is what the total energy, but how much is the energy transfer per unit area per unit second? So that will be energy into volume, but volume is what? V. So that is why here E into V, and what is the total energy we got here? 2 pi square rho n square a square, here 2 pi square rho n square a square into this V as it is, and equation number 10, and that is what the last equation, energy transfer per unit area per second. That means in 1 second this much will be the energy transferring through that particular area of cross section. This is what about energy of a plane progressive wave. Okay. If you have any doubt, then you can post in the comment box. Remaining things we will see in the next video. Thank you.